I can be like, oh yeah, I love music out right out of college. Especially nowadays, it's like, hey, just have like
Okay, sorry I'm late. Just not sure why I missed the beginning of the class. Was working on something and forgot about it completely. Okay, so last time we had Cody. Hopefully you enjoyed him. Hopefully live stream is going fine, so you guys can check on Discord if anything. Just a couple of words about the midterm, right? So we graded the midterm, and I just wanted to reflect a little bit on that. So, I mean, this is the histogram which I was shooting for, and I actually achieved it. So you might agree or disagree with the complexity of the exam, but like you can say that the max score is 97 out of 100. So there are people in the class who achieve this, come very close to the max score. So we have roughly 4 people in this 90 out of 100 bucket, right? And then we have a histogram. So I think the performance is this is what I expected. So, and I don't think it's bad or good. It's just fine. So it would be nice to have more people here, but again, I didn't expect it to be much better. Overall, I think you did well. So we have a mean of 6678. And I know that this is about the time where people start being worried about their grades, and that's why I proactively published the grading scheme on Canvas, right? So do you guys see your letter grade? So as you can see, that's a very permissive grading scheme. So I looked through it, so there are no C's or something like that yet, right? So which means that there's a bunch of A's, and probably more than in any other class, or on par with any other classes, a bunch of A minuses, right? So it's just, this is how I grade. So, but I don't think there is like any unfairness in that. It just, the exams are harder. Everything is a little bit harder. Whatever. The benefit is I see who the best people are. I hopefully can encourage you to, to do a little better, to get into that bean, because some people might think, okay, I can never get to that bean, which is like 90%. But it turns out that like several people in the class can. You can talk to them and ask them, what's the trick? Like, what is their approach to studying for this class, how they achieve it, right? And so it's totally normal. And in general, the class, I understand that the class is a little harder than what one might expect, right? In terms of it's very hands-on, like even setting up a homework is hard because you have to deal with real things like Bosch, QEMU, real interrupts, and it's all crashes underneath, right? But we'll try to help. Again, the benefit of having it is that you will go there in this world where you will be asked to do these things, for Amazon or for any other company which you choose, right? And hopefully you will have at least some background knowledge to do it. So, when someone comes and says, okay, what is your pass or what is your library pass? You say, I know, this is it. Like, that's why it runs, right, on my wonderful data center. So hope it's a meaningful trade-off for you guys. But in terms of grades, again, I think you guys will be just fine. I wouldn't worry too much. Any questions about grades or anything? Some people were asking for extension, and yeah, so we had some problems with setting up the homework. So totally, like I said, let's do Friday for now. Hopefully, if I ask people, how many people have not yet set up QEMU, meaning that they cannot, I know that you may not boot yet, but at least who set it up to make sure that, okay, who didn't? Okay, Kevin, you should catch up. It might be hard. Sorry, you mentioned the name. Okay, so yeah, please help or ask on Piazza. Today I have office hours. You can come and I will help you to set up. It's not hard if you ever done something like that before. But on the other hand, if you never dealt with anything like, build my own environment, that's a little bit unusual question.
This is sort of a caveat, and then there's an actual suggestion.
Mhm.
I accidentally started doing homework 5 instead of 4.
Mm-hmm.
And I noticed that there's a line at the very end of the first example, or the first setup, that I think could be useful to put into this homework.
On 5? Okay,
Yeah,
sure.
where it's talking about putting stuff into GDB init. I know
I
when
forget.
I was building the first setup, I ran into issues of having to need that.
Can you be a little bit more specific? I mean, you can send it to me on Piazza, and I'm welcome, or like you can even create a pull request, and it's totally.
I'm not the only one that ran into
Okay,
that.
got it. Yeah. So I noticed like a couple of days ago, I was actually going through the homework with one of the students on Friday, I think, trying to help him to debug it, right? And I noticed that the GDB, the way I set it up for this homework, is that it fixes the port 1, 2, 3, 4, which I didn't realize because I think in the past we were using private virtual VMs in which this port was available to you always. And if you're doing this on a shared machine like Cade, someone else might be already using this port. And so the real way to do that is to do the trick which x86 build system does, that they have a template and they try to list the available ports and essentially pick one which is available and just dynamically generate GDB in it. But is that what you're talking about, or are you talking about something else? Something else, okay. So you mean like put this pass, meaning saying, okay, enable GDB debugging for this program application of this pass, is that what? Okay, got it. Yeah, there is that, yeah. So there is a couple of bugs, and yeah, I mean, last time I taught this class was not this last fall, but a fall like 2021. And the world moved on a little, which I partially missed a little again. So for example, there was this issue when the grub boots you. Normally, back in the days, like 2 years ago and up until that time, grub always was leaving the system in a 32-bit mode. And suddenly on some of the machines which I've seen, unless you put this patch saying, okay, here's the 32-bit module for grub, it actually boots into 64-bit mode. And this is a funny thing because hello world actually works. That's a good question for the exam, why it works. I don't know the answer. But if you start setting up the page tables, your move instructions suddenly, instead of being interpreted as 5-byte 32-bit instruction, CPU happily takes them and says, okay, well, I'm in 64-bit mode, so I will take this move instruction. But set a 64-bit mode, instead of 5 bytes, it will be 7 bytes. And then it starts executing, and it's fun to see how, like you crash pretty soon, like on the third instruction, I believe. But still, it takes you some time to understand what you're doing. Again, it's part of this. I understand. Okay, it would be nice to click a button, everything works, but it's also part of this educational experience. Being able to debug those things. It took me some time to understand. Okay, I booted in, because you normally you don't think about what mode you're running in. You say, okay, I want to be in 32. I believe I'm in 32. The question is like, okay, I'm suddenly in 64. The way I realized that I dumped the register, right, and I understood that CPU is actually, the GDB lists 64-bit registers versus 32-bit. So any other questions? All good? The main thing which I wanted you to understand as well, or to learn from this homework, besides just booting and setting up a page table, which is of course the main narrative of this homework, is to learn how to debug with GDB. So how many people did connect GDB to your homework? Just a couple. So did anyone finish this homework without connecting the GDB? That's pretty cool. You guys are lucky, but my suggestion, try connecting. This is the lesson. The lesson is to learn, because we are not about guessing. At some point, guessing becomes impossible in this kind of work. Go try using the tools to debug. Debugging here is harder than building. And I mean, it's my life. I mean, I spent like years doing this. I usually, when I was writing code, I write like 3 lines of code a day. by any metric, it's bad, right? But that's how it is. It takes you, like, on average, you achieve 3 lines of code. It's just that they achieve so much. The semantic change is often so big that, it's enough. Your interrupt mechanism is, I mean, maybe, I don't know what the real number is, but the number was slow. Debugging was taking a lot of time. Okay, good. Any other questions? Okay, let's then go back to our lecture. So our goal today is to understand the interrupt pass. Actually, this is probably still in the future. We should probably go back somewhere here. So we first want to understand the interrupt pass when we do change the privilege level. Let me just figure out this slide. Okay, this is the one slideshow from this. Okay, so who can quickly remind me what these privilege levels are? Let's say, how many?
4, but we use only 2.
Okay, 4, but we use only 2, correct. So the kernel runs at which privilege level? 0. 0 is the most privileged. User runs at 3. Where do we keep those privilege levels? How do we keep track of them?
In case of interrupt, there is a bit for that. Also, we have CS 16-bit register, we have TPL.
What I wanted to specifically hear or remind you is the following. Remember this GDT, which I keep talking about, which is probably everyone is tired of, but this is a global descriptor table, right? And when the hardware reads, imagine you say like long jump, and you say CS and some address, right? The CS will choose an entry from the global descriptor table, right? This entry is called what is it? Segment descriptor. There will be a field with 2 bits, which will encode one of those privilege levels, right? This number, which is in that field, gets saved on the CPU, right? So CPU has some internal, we can call it register or storage or something where it keeps this current privilege level, right? So this number will become your CPL, current privilege level, right? And this is the level at which you're running. If you're in a kernel, it will be 0, right? If you chose CS with a different entry, which chooses 3, for example, here, right? Then you're running inside user and your CPL is 3, right? And also, when you do certain things, the hardware will check this privilege level. So for example, if you're running at level 3 and you decide to do long jump with a CS which tries to switch you back to the kernel, what will happen? Guess what will happen? You will get a protection violation. It's an exception, like an interrupt, right? Because the hardware will check that your current privilege level is 3. You're trying to switch to 0. Okay, this is not allowed. You can only switch back to 3, right? However, you say, okay, cool. And we'll talk a little bit about it. What happens if an external interrupt comes, like an interrupt from a timer? Then this transition will be allowed, right? And we will talk about it in a second. But essentially, the high-level idea here is the hardware and the interface of this privilege level is designed in such a manner that you lock the user level, so kind of put it in a cage, and the user level cannot escape. It can only exit this cage through a well-defined exit mechanism, which is a system call or an asynchronous interrupt, or synchronous interrupt like a page fault, stuff like that, right? But essentially, the user is running in this container. And this is kind of a powerful principle because you say, look, I have a privileged component, which is a kernel, which will be setting up multiple users. And these processes will be completely isolated from the rest of the system. And the only way they can interact with the system, roughly speaking, is invoking system calls, right? So that's the high-level idea, why it's built this way. But the details, I mean, there's a lot of, like a ton of low-level details hidden here, but at least at the high level, you have to understand that if your CPL is 3, you cannot switch back to anything but 3, right? Unless it's a system call, and we will see how it's enabled by the operating system.
If you draw the CS register, right, so we have 16-bit, right?
So in that also, lower 3 bits are specific to, I mean, lowest 2 bits is related to DPL, and one of the bits indicates IDT or GDT, right? So there we are not assigning anything related to DPL related information. We're just storing the DPL in only GDT entry. But how we map those two?
I mean, what you're asking is, what is the meaning of this two, right?
Yeah.
To be honest, I forgot.
If you store DPL in GDT entry, let's say 0, then what will be there in that CS register?
I forgot. I don't remember. Let me take it back, and let me take it. I will try to debug it, like to figure it out for you. And I forgot the meaning of these 2 bits.
The last 2 bits are related to DPL, and next one is for IDT or GDT.
Yeah. No, I remember, but the question is like what kind of a privilege level is stored in the CS register, and I don't remember. It just probably either escapes my mind or it's not used that much. But I will figure it out for you. Okay, come back to it. Thank you, Ashok. Good question. So any other questions? All good? So okay. So we imagine, like, again, we're running in user level, right? So we're ready to switch the privilege, right? So we're running inside our current privilege level is 3. We're inside user, right? So this is not what I wanted to explain right now, but okay, let's explain this. There is this, okay, that's, if you're like, the question is, so if you're running inside CPO3, so how is it what is the mechanism which allows you to switch back into kernel, right? So I keep mentioning that usually if you say, if user can invoke something like an interop instruction, something like int, let's say 13, which I believe is a page fault, it's clearly not a good idea to allow user code to invoke this interop, because it clearly confuses the operating system, because suddenly you see, so in 13 goes into the interop descriptor table and says, okay, look, clearly it's an exception, and it's a page fault exception, so I believe that user accessed some memory, but really it's not, because user just invoked this in 13, right? So normally the hardware allows you to say, okay, I will disable those interrupts, so user will not be able to invoke in 13, right? There's a subtle difference here, so subtle catch. So if you really have a move instruction which accesses the unmapped memory, then obviously you want to see an exception, right? In this case, those synchronous exceptions, you cannot disable them at all. They are always enabled, irrespective of a privilege level. If something bad happens, we have to react, right? So that's totally fine, right? So if you're touching a memory which is unmapped, the hardware will say, okay, I don't know what to do because there is no mapping for this memory. So I will go through this interrupt descriptor table and just try to invoke the handler. But in order to protect the user from invoking like just interrupts randomly, we will have a field here in the interrupt descriptor table, which controls which privilege level can invoke this interrupt. And so specifically in the interrupt descriptor table, for each entry, there will be these 2 bits, right? So descriptor privilege level, DPL. And again, you can set up, like if you put 3 here, it means that you allow user to invoke this interrupt. And if you can guess correctly, this is how you enable system calls. So a system call will be implemented. We will pick an entry. I would say it's x40. And we say for x40, we will have this field set to 3. And the user will be invoking x40 like this. And that's a transition from user to kernel, right? Remember, I said we try to lock user in a cage. So the only way to escape this cage is to essentially, for the user code in x86, is to invoke an interrupt 40, for which this field is set to 3. However, the operating system sets this field to 0, and for example, let's say for the vector 41, if user tries to invoke x41, it gets a protection violation because this interrupt transition is not allowed for the user, right? Does this idea make sense to you? Any questions? So it's essentially a mechanism to make sure that users cannot just randomly invoke in something instruction.
So you're making DPL as B when you're running on user mode, right? But the offset, whatever we have in two places, that will be the address to interrupt handler.
Correct. This will form the 32-bit address of the interrupt handler. This will choose a new segment, code segment, right? Okay, so it will become clear in a second. So just, I forget exactly why I kept this slide here. There was some line which I liked in the past, but let's just take a look at how it works when you run CPL3. So again, so I have a line here. So below is the kernel, privilege level 0, and above is user, privilege level 1, privilege level 3, right? So this is user stack, for example. We're executing some user instructions, so in the user memory, right? So your instruction pointer is pointing somewhere over here, right? This is the user stack, right? So stack of a process, as I was saying. So similar layout. So some arguments were passed to the user function, which we're currently executing. We save the return address on the stack. We save the old frame pointer. There are some local variables allocated on the stack. There are some saved spilled registers which you pushed on the stack as well, right? So imagine you're running something like cat, right? I don't know, cat or alas or something, right? In user level. Imagine at this point, a timer interrupt shows up. The hardware triggers a timer interrupt. So what is a timer? Timer is a piece of hardware, which is the physical piece of silicon. I don't know real the physics, but there is some kind of a quartz thing which allows you to generate ticks with a specific frequency. And at some point you can program it and say, okay, let's say 10 times a second, please raise an interrupt. What does it mean? It's just raise a signal on a specific, which is connected to a specific pin of a CPU. CPU reads this pin and says, okay, I got it. So like I have an interrupt. And the internal logic of a CPU at some point says, okay, remember this fetch, decode, execute loop. It says, okay, instead of executing that instruction, I have to really react to this interrupt. And the timer is on x86 is connected to interrupt number 32, right? What do you think happened next? What do we need to do? Remember, in case when we don't switch the privilege level, we have to save certain things on a stack, right? So what were those things? The registers which are immediately changed on the interrupt transition. Instruction pointer. Yeah, what else? Yeah, CS, and what else? E flags, correct. And so these three things are immediately changing, and so that's why the hardware provides you a way to save the old original values, because when you transition through the interrupt descriptor table, you choose a new code segment, and so it like overrides the old one. You choose the new instruction pointer, right? So you lose the value of the old one, and you also might alter the value of the eFlags register by saying that the further interrupts are disabled, right? Because again, this is how you can set up the interrupt descriptor table. And normally, remember, I was saying that we're gonna just save it blindly here on this stack, right? Agree? Okay, the question is it safe to do that in case you're running in user level? Can you save those old values here? So this is like ESP pointer points here, for example. Might what? What is the attack here?
You might overflow the stack.
You might overflow the stack, meaning?
You're right at the very end of the stack. You only have 1 or 2 bytes left on it. And now you're trying to push 12 bytes onto the stack or 24 if you're 64-bit mode, not enough space. And so you're in the middle of doing an interrupt, and all of a sudden you get a page false.
Okay, yeah,
So
agree.
you get 2 faults in a row, and then the processor doesn't know what to do.
Okay, you're right. Let me explain this story. Imagine this is your stack page, right? And imagine the next page is not mapped. Just there is no entry in a page table. So if timer interrupt comes, and imagine user is malicious or maybe accidentally malicious, meaning that somehow the ESP is at the very top, at the very bottom of this page, right? And so the moment you try to save the three things, it actually goes into the next page. The next page is not mapped. The hardware doesn't know what to do. It goes to the page tables. That's your implementation as a CPU designer. You build the hardware to follow this protocol, try to figure out the mapping for this page, right? Mapping doesn't exist in the page table. The hardware says, okay, like, I don't know what to do. Logically, you say, okay, I will generate a page fault. The page fault itself is an interrupt. And you say, well, I need to save these three things again. But at this point, you say, okay, well, it's again the same story. And so it's a double fault. And at this point, the hardware says, okay, it's a triple fault. And at this point, I have no way of correcting this action. I will just simply reboot. That's how x86 reacts to it. That's one attack. So the kernel just simply reboots, right? Can you come up with a more sophisticated attack where you get control over the kernel? It's a actually good exercise for kind of a security class. Or so this one way, we can classify it as a denial of service attack. So I don't know, on a timer interrupt, your machine reboots. You started the process, you crafted the stack in such a point that it points to the top of the page, you looping in the infinite loop, wait for this 1/10 of a second or 1/100 of a second, depending on how it's configured, and your machine reboots. That's success. If you know you can reboot all machines in the world, you probably can create a lot of harm. But can we do better than just this attack? Can we do something really nasty?
So I suppose that if you had another thread or something that's in that same process, you could modify those values on the stack. And that, since now you're restoring the CS to whatever's on the stack, you could actually get into a different privilege level than what you're supposed to do.
I think your line is not fully complete, but the direction in which you're thinking is right. So I don't know why you mentioned a thread, like multiple threads will run in the same process, though supposedly they all are with user privilege, right? But what you can do if you say that if the hardware blindly follows this protocol, why not to put ESP value to point somewhere in the kernel? And the hardware will just blindly override your kernel memory. And then if you're careful enough and you can play with the value which you want, then you will just, you can maybe flip a bit in a page table, or you can flip a bit on Linux. If you have a privilege process ID, you can flip it to a magical super user ID, right? And stuff like that. So it gives you a write primitive, right? It's a limited write primitive because IP has to be a certain value, which might not always work for you. But nevertheless, you can write kernel memory, right? You get it? So like this is how the modern attacks work. So that's one way to do them. If you have a write primitive, you're powerful. You can maybe overwrite some value on the kernel stack, and then the kernel will start when it does a return, it will do something else. Instead of returning to a proper call site, it will just go somewhere else and do something, right? Okay, so this is clearly not right. So you cannot save values on this user stack. I'll ask you a question. So how we can fix this problem? We definitely have to save those values, right? So, but how? What do we do? What are the ways? Store in kernel stack. So what does it mean? So what we need to do is we need to come up with yet another stack, meaning that really each process will have a user stack and yet another stack, typically empty, waiting for it in a kernel. And when the interrupt comes, you say, look, instead of saving those three values, I will save them there on this kernel stack. Because if the operating system controls the location of this kernel stack, then it's always safe, right? The kernel, you as a kernel designer will make sure that the stack is allocated, is not close to its capacity, so you will never run out of stack space, right? And this seems to be safe. The question is, where do you think, how can you locate this stack? So essentially, if you say, look, I know that the process has a user stack and it's pointed by the ESP register, I need this value to figure out where the kernel stack is. So the hardware will follow this protocol and figure out where to save these values. So as a CPU designer, what kind of interface you would provide to the users to do this? Well, there is no real magic. You can do a bunch of tricks, but what x86 is doing is it follows it says, okay, there will be yet another table, which is called TSS, or task state segment. And this table has a bunch of values which were used in the past, but almost never used today. But the only values which are used today are used to locate this kernel stack. So there will be a stack segment and a stack pointer, right? And again, everything has a segment, so that's why we have a stack segment. And like ESP, we usually call them 0 because it's ESP for the privilege level 0, will allow you to establish this pointer. I mean, you meaning the hardware will follow this protocol, right? So, okay, let me just quickly walk you again through the interrupt transition pass so everyone just is on board. So when the interrupt arrives, right? Remember, fetch, decode, execute the loop. The hardware, instead of executing the next instruction, does the following. It says, okay, I know that there is a pointer to the interrupt descriptor table, and since it's vector number 32, like the hardware has IDTR, meaning that it's interrupt descriptor table register, which is loaded by the operating system. So it locates the IDT interrupt descriptor table in memory. It's a virtual address. Then you say it's an entry 32, which allows you to select entry number 32 from the table. From that table, from the interrupt descriptor table, you read two values, code segment and the offset, meaning that you say, okay, I will go to the GDT and figure out my new privilege, because if we're running at CPL number 3, for example, you want to choose an entry which will have a privilege level 0, because this is what you want to choose, right? And so the hardware will load this entry. Your CPL switches from 3 to 0. Then you take the offset from this table again, which points to the memory, which is the entry point of the interrupt descriptor handler in the kernel memory. And the hardware will set your instruction pointer to the beginning, to this value, to start executing this handler right after this interrupt transition. And it also says, okay, I know that I have to figure out this the new stack. And so these two entries in this task stack segment TSS will allow you to choose the new stack segment and a stack offset in the kernel memory, right? And so the hardware then will save those 3 values here, right? So it was EIP, code segment, and E flags, right? However, you need to save a little bit more. What do you think you need to save? What values have changed in this transition when you switch between privilege levels? What?
User level ESP.
Correct, because since in the first example, ESP was just linearly growing. When you don't switch the stacks, you say, I will put something on a stack, and when I do the IRAT, I will like essentially just pick these 3 values from the stack and my ESP will be restored. But now this old value of the ESP needs to be saved. And since again, it's accompanied by a stack segment, so you have to save this too. You have to save ESP, this user ESP, and the user stack segment, right? So when you switch privilege level, everything is almost the same, but you switch to a new stack and also save 2 additional values on the kernel stack, right? And then you start executing in a kernel. Good? What about DS? What about DS? That's a good question. And I should admit, I don't remember. So the idea is that you can let me take it offline as well, just not to be stuck here. So can you ask this on, so this is the second question. What about What about DS? That's a good question, and I don't know the answer. So which means that you should get an extra point, like for your final grade. If you can ask me a question which I don't immediately know the answer. What was the first question? I forgot. Yeah, like what are those two fields in the descriptor, like code segment, for example? What are those two fields, right? What is the role of those two fields, right? Let me dig them up. If you can ask me on Piazza, I will answer. Okay, forget about DS, right? For now, I believe that you can just save and restore DS, and there is enough machinery to make sure that you can do it. But that's a good question. Still makes sense to explain. Okay. So as I was saying, task state segment, bunch of fields. We don't really care, but what we only care about are those two fields, stack segment and the stack pointer in a kernel, right? And the processing of interrupt pass when you transitions between privilege level will be the following. So you again, like save your ESP and stack segment internally on the CPU for a while. You load the new stack segment and new stack pointer from the TSS. You push this SS and ESP, E flags, user code segment, and user EAP on the stack, on this new kernel stack, which you located here. You get the code segment and instruction pointer from the IDT, right? Because this is where your handler is. This is where you put the location of the handler. And if there is a special flag in this interrupt descriptor table, you disable the further interrupts in the eFlags register, and you start execution of a handler. So this is the protocol. This is from the Intel manual, roughly speaking, which essentially tells you what the CPU will do when it will transition between interrupt levels. And the stacks, essentially, if this was your ESP before the call, right? This is the user stack, and this is the handler stack, which is a kernel stack. Those 5 things get saved on the stack. So SS, ESP, eFlags, code segment, EAP, and some interrupts will also push the error code, right? But it's a different stack. So now you have 2 stacks, user and a kernel. And the difference is this. So like if there is no privilege level change, then you would push these values, and only 3 values because ESP and SS are not really changing. You would push them on the same stack. But here you pick a new stack. Okay, and this is the complete interrupt pass. If you ever, the reason you will need it is that the next homework will be extending x86 operating system kernel with a new system call, and I will prepare you for that, so don't get scared. But essentially, this is the diagram which you have to keep in mind. So essentially, this 5 things get saved here on this kernel stack.
So I know, like space-wise, they're basically the same, but what is the user states part in stack? Is it stored on the kernel side of the stack, or is it stored at the user side and then the kernel right below it?
Wait, you lost me. Can you ask again?
Yeah, I know space-wise, they're basically the same stack. They're all the same stack, but just sort of for my brain's sake, is the SS, ESP, eFlag, CS, EIP, is that considered kernel stack, or is that user stack where they're stored?
This is the user stack, right? Some location in memory which is which is mapped with user accessible privileges.
I'm talking about after we've stored the values when we're entering.
So then,
are they stored in the kernel stack at the top?
Right. So this stack will be sitting somewhere here in the kernel space, which is usually sitting there idle, doing nothing, and it's just always ready to start executing inside the kernel. We'll talk more about it, and you will see the role of this stack. So it has an additional role of like saving the kernel, the process state when you switch from one process to another. But you lost me a little bit with your question, so I'm not really. Okay, got it. Okay, so this is like a good diagram. So if you ever need to know what's going on the interrupt transition, you start from here. This is the interrupt number, and follow those lines, and you will be able to figure out what is happening. So if ever you do a job interview and someone asks you, what happens on the interrupt, you quickly remember this figure, and if you understand it, then you will be able to answer the question. Okay, let's talk a little bit. So I kind of gave you the overview of what happens, but let's just fill in the gaps and just understand what is there in that interrupt descriptor table. And again, there was a chicken and egg, and maybe I should have started with this table, but I started with transitions, so I'm not really sure what's the right way to go about it. So, but on x86, the table itself contains 256 entries from 0 to 255, right? The first 32 are reserved by Intel. So Intel says, okay, those are mine. I will control those numbers. I will define the semantics. Like, for example, maybe interrupt 13, and on the next slide, I will have exact numbers. It's a page fault, right? If you access an unmapped memory, I will generate an interrupt number 13. If you, like, there is something that is called non-maskable interrupt, it's vector number 2, for example, right? So Intel, the CPU manufacturer, tells you what it is, right? The next 32, or sorry, the next 16 from 31 to 47 are called IRQs. And you probably have heard this term. It's, what is it? Interrupt request. I forgot what Q stands for. Doesn't matter. But essentially what it is reserved, it was reserved by devices. So when I was a kid and computers were still young, you sometimes buy a new piece of hardware, like an audio card, and you have to configure, like on the card, you have to like switch something what is called a jumpers, essentially just connects two wires saying, okay, you will be attached to interrupt number, for example, 35. And if you have something else already sitting on 35, you have to pick a different interrupt. Right now, the software sorts it out automatically underneath, but typically, like it's still some legacy devices, like for example, timer. Remember, I keep saying that timer is interrupt number 32, and it's really like this is the legacy back traditions. Essentially, the timer is still running on interrupt 32. I'm pretty sure that modern days you can come up with different timers and you can reprogram which interrupt they're going to deliver, and the operating system can tell you, okay, deliver me something in this space, right? And that will be your timer, maybe high precision timer or something like that. But typically it's reserved for devices, right? And those IRQs, the naming is that it starts with 0, but since it starts in a table, it starts with position 32. So IRQ 0 is the interrupt number 32. It's not important to remember right now. It's a low level detail, but maybe later on you will see a piece of code which says IRQ, and you know that, okay, this is what they mean, right? And those interrupts are open. So essentially on your system, depending on which kind of hardware or software you have, the operating system kernel can configure those and use them at OS's discretion, right? So essentially you say modern days, if you have network cards, you say, look, okay, got it. So when you will be receiving packets, I will instruct you to generate an interrupt, let's say, I don't know, like 64, right? Or since 64 is actually X40, and it's a bad idea, but you say, well, this my interrupt 64 will actually I will be using it for a system call, right? So if user invokes int 40, the operating system will react in such a manner that, you know, it will be a transition in the kernel and it will execute a system call. And we'll just take a look at how it works in just a second, right? Okay, so here's this another view of this table from the Intel manual, and that was wrong. Let me just go back here. I was just trying to move this. So as I was saying, so some interrupts are defined by Intel, the first 16, the first 32. So for example, interrupt 0 is a division by 0, remember? Right, I told you that, okay, the hardware wants to do it. There is a debug interrupt, so essentially you have a hardware mechanism to ask hardware to essentially figure out when you access a specific instruction pointer or you access a specific value in memory, address in memory, and it will generate you an interrupt, right? So it's actually called I don't want to hang out here, so maybe I'm wrong a little, but like along those lines, we can read out the manual. So non-maskable interrupt is number 2. Breakpoint, like essentially you can this is how GDB works. So when you say, I want to install a breakpoint, it essentially, imagine you have a move instruction and you say, I want to install a breakpoint on this move instruction. What GDB is doing internally, it says, okay, I got it. It's a move instruction, it's 5 bytes. But what I will do, I will replace this first byte with a specific instruction, which is called XCC. I just happen to remember the number. And this instruction is actually, it's int number 3, right? Meaning, when you reach this point in your program, instead of executing this move instruction, since you replaced it with int 3, you will go through the interrupt descriptor table into the operating system kernel. The kernel says, okay, I got it. So this is the GDB attached. I know that GDB is trying to understand, like help you to understand what's going on in this program. And at this point, the kernel will pass control to the GDB. GDB means debugger, GNU debugger, right? Which I'm asking you to use in those homeworks, but it can be any other debugger. But essentially, this is the mechanism, right? And so this way, the GDB says, okay, I know we will reach this point in the execution, and there is also a mechanism which allows you, please single step the instruction. So GDB says, okay, I remember that I replaced move instruction with this XCC, so I will temporarily put this byte back and let the hardware to execute one instruction. There's this mechanism, and again, it executes this one instruction, gets exception back, shows you what changed, and this is how essentially breakpoints are implemented. Did you get this high-level story? I mean, we can come back to it, but this is what's going on. So sometimes if you start dumping, if you installed a bunch of breakpoints and your code essentially dumps the memory, you will see those CC instructions, right? And this debug exception is slightly different. It's like specific hardware support, which allows you to not only monitor access to a specific instruction pointers, but also say, okay, for a move instruction which touches this address, and you have a thing you can configure 4 of them at a time, please generate an interrupt, right? There are some additional exceptions like overflow, and bounds. It's like there's a specific instruction which checks the bounds and can trigger this instruction. Undefined UD2 instruction or is reserved. Essentially, if you have an opcode which is undefined, you will trigger this exception. How it's used in modern systems is, for example, in Rust, when Rust wants to implement panic, instead of like doing a system call, it just often inserts this undefined instruction opcode and just forces the hardware to trigger an exception on x86, right? So if you see it in the code, don't be surprised. Remember my 7 means that there is a coprocessor, like floating points. It used to be a different physical piece of hardware, which was like a GPU, like a different piece of silicon. And this is an exception which hardware was sending you when you say, I want to use it, but it's not really available in your system. Roughly speaking, like GPU is not available. Double fault, remember, we talked about it. So if you do a page fault and suddenly the hardware cannot really transition, or while doing this fault, there is another exception because maybe there is a bug in your IDT and it points to nowhere, right? Or bug in your TSS and there is no kernel stack, for example, or it's unmapped, you will get a double fault, right? So just again, when you will be debugging your homeworks, I'm pretty sure you'll be seeing double faults. I don't remember 9. 10 is like, again, bug in a TSS. Forgot 11. Like literally don't remember 11, 12. 13 is a general protection fault. I kept mentioning it's, for example, you trying to reload CR3 from user level. And remember, I told you that access to the control registers from user level is disabled. So if you try to use this instruction, you will get general protection fault. Page fault, I was wrong, not 13, but 14. This is exactly like we talked multiple times. We mentioned it multiple times, right? 15 is reserved. Alignment check, remember I said that we have to, GCC, for example, the GNU compiler and other compilers align the stack to a 16-byte boundary, right? Because some instructions require a specific data alignment in memory, right? And if you break this alignment, you will get an exception, right? Machine check, it's typically something horrible happened, like, the CPU is overheating. Maybe you're trying, I don't remember exactly what the conditions are, but like, for example, you might access physical memory, which is not present on the bus, like generate an address, which is not there. You will get a machine check instruction, right? So 13 and last one, 19 here, don't really remember. SIMD, it's a set of vectorized instructions which are typically used in graphics processing, and today are used in more generally, like to optimize operations. If you can execute multiple operations in parallel, then you will use this as SIMD instructions. But what kind of exception they generate, I don't really remember. Okay, as I was saying, those are reserved. Then IRQs from 32 to 47, and then the rest is open for you to use, right? Any questions about this table?
So are they mostly exceptions then? And very few, like interrupts, like 3, for example?
Yeah, all of these are exceptions. They are synchronous. Almost. Meaning that non-maskable interrupt can be asynchronous. This one, number 2. And non-maskable, you can kind of guess from a name. I mean, I don't know what. Masking an interrupt, meaning because you set a mask in a register, means that you're disabling an interrupt. So this interrupt number 2 does not obey this logic. And the hardware will, no matter, even if you disable the interrupts, the hardware will still deliver this non-maskable interrupt. It's reserved for those special cases when something is so critical is happening that you have to react no matter what. Hardware will deliver only one non-maskable interrupt. The second one will be suppressed. So you have a window of time when you're going to be processing this non-maskable interrupt, in which you will not be preempted by another non-maskable interrupt. But it's kind of interesting that there is this kind of always a backdoor. You say, look, I disable interrupts, but first, of course, exceptions will always happen because they're synchronous. And the hardware can deliver this one asynchronous interrupt to you, which is non-maskable. It will not deliver timer, it will obey the E flag, which masks the interrupts, but it will deliver this non-maskable interrupt. And so, for example, the way I've seen, like you can configure different things. I think there is an interface which allows you to configure any asynchronous interrupt, I think, to be non-maskable. But what specifically it does, like I've seen it used is, for example, you have like, if you ever do performance analysis and you know such tools like iPerf or vTune, they collect hardware events and they keep counting how many instructions, for example, you executed. And at some point they use some internal buffers which say, okay, they have limited capacity. At some point it says, okay, I'm reaching the limit of this capacity, which means that if you don't flush this buffer or give me a new one, we will miss some information. And then it delivers this non-maskable interrupt to give you a chance, to give operating system a chance to react. But you're right, so this is a good observation. All of this, Intel typically reserves only exceptions and everything else is kind of open. So those are some critical conditions to which says, okay, we have to react no matter what. If you're dividing by 0, we have to do something. And so Intel gives you an interface. Any other questions? Good. Okay, so we have the table, page fold, yeah. Just another description of this table. As I was saying, to disable an interrupt, you set a flag, which is called interrupt flag in the eFlags register. As I was saying before, these critical interrupts, which are exceptions, which are synchronous interrupts, cannot be disabled, right? It doesn't make sense to disable a page fault because, you know, like, there is no way, like, okay, what does it mean to disable a page fault? Magically make up a page out of somewhere, it doesn't work. Instruction itself, int, like if you have your code says int 22, this will also, like it's a synchronous interrupt because you invoke it from the code, it will not be disabled by the eFlags. But all asynchronous interrupts can be disabled with this flag, besides one, which is this non-maskable interrupt, which is entry number 2 in the interrupt descriptor table, right? So we just discussed. And this is reserved for some critical events like, you know, I don't have power, we have to shut down, stuff like that. This is NMI. But as I said, the hardware will deliver only one of them unless you until you return from it. So you have a window of time. Okay, so now we still have 20 minutes. So we know how interrupts work in general from the CPU side. That just take a look at how you as a system designer essentially use this interface to configure the interrupts. Essentially create a new interrupt descriptor table, create a first vector, or like create vectors and essentially work with this interface. And again, this is the part of your homework. It will be copy paste, so essentially take existing code which does something with interrupts and just extend it with one new interrupt. But essentially to be able to do the homework, you need to understand like how they work at a high level, right? And at the level of the source code as well. Okay, let's take a look. So again, we're back to this main function. So I have a label here for you. And this function initializes the trap vectors. Trap is yet another name for an interrupt. Back in the days, people like to distinguish traps, exceptions, and interrupts. Today, I would say if you say exception and interrupt, you're golden. Exception means a synchronous interrupt. Interrupt usually means asynchronous. And if you forget, just say any of those terms, and normally the other person who is doing the kernel work will understand what you mean, depending on the context. So don't worry too much about remembering distinguishing all three. As I said, okay, when we're booting, we remember the first thing the kernel does, the very first instruction which we're doing. Who remembers which one is that? In the kernel? Disabling the interrupt, right? It's a CLI, so clear the interrupt flag. And so interrupts are disabled because we didn't have this table set up. And so what we're doing here, we're setting up this table. Remember I said it's like from 0 to 255, and we use a macro which essentially says, okay, this is an entry I in the interrupt descriptor table. What you're putting here is the following. We actually doing the following. We do the 255, and then we overwrite one special one, which we're going to be using for a syscall later on. And the only difference between these two is this field, right? Let's take a look at those fields in more details, right? So as I said, in general, we're setting up the page table or the interrupt descriptor table in such a manner that the user code, which runs at privilege level 3, cannot issue something like a page fault in 14, because that will confuse the kernel, right? You don't really know whether was it a legit page fault or it's just like the user is malicious and it compiled the program which tries to invoke it, right? And typically we disable invocation of this interrupt. And the way we do this is we configure this field in the interrupt descriptor table entry, right? We set it to 0, saying that the transition will only be allowed if your current privilege level, CPL, which is, for example, 3, is less or equal to descriptor privilege level. So if it's 3 and the DPL is 0, the transition is not allowed, right? If you're currently in the kernel, then it's fine, right? Or if we're trying to open up one of these, we will set this field to 3, and then the user can invoke this interrupt with int x40, and we will use this interrupt as a system call, right? Let me explain how it works. Essentially, what we've done here is say, okay, actually, man, I was wrong. It's not this field, these two fields. It's these two fields. So this essentially DPL 0, and this is DPL user, which is set to 3, right? So all the entries in a page in the interrupt descriptor table are set to essentially have DPL 0, and one entry which we use for a syscall is set with DPL 3, right? Which means that user will be able to invoke, if this is x40, then user will be able to generate x40 to invoke a system call through an interrupt transition mechanism, right? Okay, so what else we're setting here? So we say all entries, for each of the entry, we will have a pointer, which is a vector which we want to execute, right? So essentially, this is an offset, which we're filling in the table. And remember that we have to choose the, because our goal is to transition from user to kernel. So the entry in the GDT, which we're choosing, is an entry which we configured. So this code segment is set to be kernel code, which means that we will transition from whatever level we were to level 3, right? And this flag remember I told you several times that this flag allows you to essentially say whether allows you to configure the interrupt descriptor table in such a manner that the subsequent interrupts are disabled or enabled. So essentially, if you set 0 for all interrupts but the syscall, you set them to 0, meaning that further interrupts are actually disabled, meaning that the hardware disabled like delivers an interrupt, and the subsequent interrupt will not be delivered until you IRET, return from an interrupt. It makes sense. It allows you to, for example, process a network packet without being interrupted, right? And like not worry about, like interrupts which are arriving on top of each other before you even like able to process them. But for a syscall, you say, okay, hold on, like syscall is more like a system call. It is more like a function call, so I don't really care about disabling the interrupts. I'll just move on forward, and if the timer interrupt arrives, it's totally fine. I will process it, right? Because the idea is that, okay, it can stay interruptible. And if you need to disable interrupts for a short period of time inside this syscall processing pass, you can do that later. Okay, that's how you configure this table. Do you guys have any questions about it? So it's more or less intuitive, right? So I mean, there are many details, but you can see, okay, like it's a table, 256 entries. One is magical, is a syscall, can be invoked from user. Nothing else can be invoked from user, and everything else disables interrupts, but this syscall interrupt. Question?
3323 line number, right? That will be used for system call, right?
Correct.
They're using DPL user as a 3 value, right?
Correct.
But in case of timer interrupt, then it should go from user to kernel, right?
Correct.
Then in that case, which entry we need to map? In that case also we have to use the DPL3 only, right?
No, because external interrupts, which are delivered from the hardware, and synchronous interrupts, which are magical, the ones which Intel reserves, are always enabled, and they will always be, like, it's not essentially this field which says, okay, this only controls if you say, are you allowed to execute int some number, right? That's what we control here. But if the hardware delivers interrupt, it will always push you. It will always push the interrupt transition. And the interrupt transition says, okay, look, I'm going through entry number 32. Entry number 32 is one of these entries which were configured in this loop. It will choose the code segment, which is the kernel code, and your current privilege level will be chosen by this entry in the GDT. And since we put the entry which chooses the CPL, the descriptor with privilege level 0, your CPL will become 0, transition from 3 to 0. Same for the page fault, same for all these exceptions which are reserved by Intel, because this is how we configure them. They always drop us in the kernel. And that kind of makes sense, because you say, if I want to patch the page table, I need kernel privileges. And even the syscall will transition us from user to kernel, because we leave the same field. We say, look, we allow you to transition from user to kernel, because we said you can invoke this entry. So you are allowed to invoke int syscall, where the syscall number is x40, right? And it will transition you from user to kernel. That's the only way for user to trigger this transition. I mean, when I say only, you can say access unmapped memory, you will generate a page fault. So this way the user can also transition in the kernel. The question is like, will it terminate the process? Most likely. Any other questions? It's a little unusual, right? Because there is like many things come together in one table, and like privilege levels, control over whether you can transition between privilege levels, hardware which sends those interrupts and says, okay, look, I can deliver them, and sometimes you can disable them, sometimes you cannot. So it gets a little tricky. But okay, sure. You have the table. This is where I put the midterm slide, thinking that we're already here. And now let's take a look at how can you design the vector itself, right? So essentially, what is the interrupt passed through the x86 kernel? Essentially, what kind of code you will be running? Because I said that the vectors or the interrupt handlers are kind of the same code, but there is a little bit of magic, assembly magic, which you need to use to make sure that you can completely save the state, right? So as I was saying, like right now we looked at how we can configure this table, right? This 255 entries. And the field we care about is this pointer to the vector. We initialized it as vector I for this table, right? And the vector I, or in this example, vector 32, is some code in the kernel. The question is like, what kind of code we put there when we build operating system? We actually use this assembly sequence, which we generate automatically from a Perl script. And the sequence is like for every interrupt, for every vector, we'll use the same sequence. We say, okay, we will make sure that in order to make sure that the stack has the same layout for all interrupts, for the interrupts which don't push the error code, we'll add additional instruction which pushes 0 on the stack, right? So it's like error code 0. Then we push the interrupt number 32. And then we jump to a function which essentially is common for all vectors, right? What it means is that what we've done here is that we saved the interrupt number and went to a single dispatch function, this all traps. Like vector number 1 will look the same. So vector number 1 will push error code 0, and here it will push 1, and then jump to all traps. What do you think you have to do inside all traps? If this is your entry point in the kernel after the interrupt transition, what will be inside this all trap function?
So we got the switch statement to decide which thing process according to the
Correct. Deeper on, there will be a function which is called traps, which will have the switch statement. But do you think something needs to happen in between these two? I will ask differently. Do you think you can implement this function in C, or you still have to use assembly?
You have to save registers.
Exactly. You have to save registers. Why?
Because you're going to be returning back to a function, in some cases, that didn't know that it interrupted even the call. And that's got to have its entire state restored.
Correct. So, I mean, like this is exactly true, but what are those registers? Those user registers, user general registers like ABX, EAX registers. Remember, the hardware saved only stack, ESP, and saved EIP, right, on the stack. This is what the hardware saved. But all the other registers like EAX, EBX, and so on, if you want to restore them, which is probably your goal because you want this program which was interrupted with a timer to keep running, right? You need to restore them, right? In order to restore them, you have to save them, right? In order to save them, C doesn't allow you to save registers. Like C doesn't know anything about registers. So you have to write this in assembly. And that's why you say, look, I first will save all the registers inside the all traps function. And essentially right now, if you jumping in this all trap function, you have this 5 registers saved by the hardware when it went through the interrupt descriptor table. These 2 things are saved by your vector 32. You push the error code here and push the interrupt number 32 here. You jump to all traps, and what all traps is doing, it says, okay, I will first save all the segment registers like DS, ES, FS, GS, right? By the way, you were asking, Ashok, you were asking about what happens to DS. This is what we're doing. So we're saving it, right? So that's why we don't have to say, we have enough of freedom to do it in software. We don't need a special hardware support. We just simply use this instruction, which saves the current value of the DS on a stack, and we will restore it later, so everything will be fine. And it's not just DS, it's all these registers, ES, FS, GS. If user was using them, we'll save them and restore them, right? And we use this assembly instruction, which just says push all, and push all saves all general registers. Like in a specific format on a stack, doesn't matter, like essentially it's equivalent to like, you can do it individually, just push all is a little bit faster, and you essentially save EAX. You first temporarily save ESP, the current value of the ESP, then you push EAX, ECX, EDX, EBX, then you push this temporarily value of ESP, just because you want ESP to, like the way you save it, you save the value which was pointing here, then push EBP, ESI, EDI, right? That's essentially what this instruction is doing. And if you care, you can open this link and you will check that push all is exactly this instruction. And so your stack now looks like this. So you say, this was saved by the hardware, there's 5 things. The vector 32 saved the error code and the number 32. All traps essentially save DS, ES, FS, GS. And all general registers, I compress it to a single line here. And at this point, your ESP is actually pointing. Okay, hold on. I draw it that let's forget about for a second. So let's see what's going on. This is something what we don't yet know. It's per CPU data structures, but your goal is to get out of assembly as fast as possible because everyone is tired, right? It's almost the end of the class. So if you end inside the assembly, you will have nightmares. But what we want to do is we want to invoke a C function trap because this is what we want. We want to get away from assembly as fast as possible. What we want, the trap is a function which takes a specific, trap is a function which take a pointer to a specific data structure on a stack, which is called trap frame. It takes a pointer. It's like, so this is the signature of a function. So it's a function with a single argument, which the argument is a pointer to a data structure, which is defined as, which is called trap frame, which has exactly the same layout as the one which you created on a stack. So like if you say, if I want to access the structure in C, I will create a struct definition, trap frame. And it will have the layout which matches the layout of these things on the stack. Which means that you say, look, I want to pass it as an argument inside my C function because I want to access the values of those fields. I want to see the user value of the EAX register, which was saved as part of those registers here, right? So how do I pass this inside the function? Remember the calling convention. It has to show up as an argument on the stack, right? And this is what exactly I'm doing. This is my argument. If I push the current value of ESP, which is here, on the stack itself, it will save the old ESP with this pointer. And my current value of the ESP will be pointing to this value. This is like, okay, sure, the calling convention. Remember, we spend a fair amount of time. And so this is what my code here is doing. It's not mine, but code of x86. I will push the current value of the ESP on the stack. And then I can call the trap function, right? Do you see this trick? So this is where you're using the calling convention. You say, I know that the calling convention in C is such that the first argument has to be saved on the stack. If the argument is a pointer, I push that pointer on a stack. And it happens to be that I'm trying to pass exactly this struct. And now you land in C. And this is the switch statement which you were talking about, and we will essentially discuss it later. So I will go over through this Interop Pass to remind it to you on Thursday, but essentially I will leave you here and we'll come back and figure out what the kernel is doing with the interop later. But you can kind of have an idea that it will, if it's a timer, it will do something. If it's a system call, it will do something else, right? Okay, let me stop here. So I'll see you on Thursday. So the homework, I moved it to Friday for now, right? If you will need more time, let's see how it goes, but we can move it a little bit more as well. Thank you.
That a big,